Hello, my name is Armand, and today I'll be presenting the Perron-Frobenius theorem. This is actually a theorem that appears in my research of the PageRank algorithm, so I wanted to do my presentation on this as it gives me a chance to kind of learn more about the theorem itself. This is a result that appears a lot in linear algebra, and it describes the behavior of matrices where all the entries are positive. And it also appears in many applications, such as probability models, network analysis, and of course, most notably, the Google's PageRank algorithm. So I'll be touching on those a bit in this presentation. So to first go over kind of the overview of this presentation, I'll begin by explaining why positive matrices are interesting to study. Then I'll introduce the definition of a positive matrix. I will state the Perron-Frobenius theorem and go over the main idea behind its proof. After that, we'll look at a simple example that illustrates the theorem in practice. And then lastly, I'll discuss how this idea appears in the PageRank algorithm that is used by Google. So first, let's talk about why positive matrices are important. Matrices with positive entries appear in many real-world systems. One example is Markov chains, where entries represent the probabilities of moving between states. They also appear in network analysis, where nodes in a network can influence one another. But the most influential and famous application is Google's PageRank algorithm. This basically models the web as a network of links between web pages. And the Perron-Frobenius theorem provides the mathematical guarantee that this ranking method produces a stable and meaningful result. So before stating the theorem, we need to talk about the definition of a positive matrix. So we say here that a matrix A is equal to A sub ij is called positive if every entry in the matrix is strictly greater than 0. So in other words, each element A sub ij satisfies A sub ij is greater than 0. So this property is important because it means that when the matrix multiplies a vector, every coordinate influences every other coordinate. So in a sense, the system becomes fully connected, and this can lead to a stable long-term behavior. Now we can state the Perron-Frobenius theorem. Suppose that A is a positive square matrix, and we can actually tell three important things from this theorem. The first thing is that the matrix has a real eigenvalue, lambda 1, whose magnitude is larger than that of all the other eigenvalues. We call this the dominant eigenvalue. Second, we say that there exists an eigenvector corresponding to this eigenvalue whose entries are all strictly positive. Third, this eigenvector is unique up to scaling, meaning that any other eigenvector associated with this eigenvalue must simply be a scalar multiple of it. So these properties are essentially what make the theorem so useful in many applications. Now I'll briefly explain the main idea behind the proof. So suppose we start with a vector x where all the entries are positive. Now we repeatedly multiply this vector by the matrix A, and this produces the sequence of x, ax, a to the power of 2x, a to the power of 3x, and so on, as mentioned here on the slide. Because every entry of A is positive, each multiplication spreads weight across all coordinates of the vector. So in other words, each coordinate begins to influence the others. As we continue this process, we say that the direction of the vector gradually stabilizes. So the magnitude of the vector may change, but its direction begins to kind of settle towards a fixed and stable direction. Eventually, the sequence approaches a vector v that satisfies the equation AV is equal to lambda 1v, and this means that v is an eigenvector that corresponds to the dominant eigenvalue, which is guaranteed by the Perron-Frobenius theorem. And again, dominant eigenvalue was just stated right before on the previous slide as the matrix whose the matrix has a real eigenvalue, lambda 1, whose magnitude is larger than that of all the eigenvalues. Let's look at a simple example. In this case, we'll use a stochastic matrix, so each column sums to 1. From the slide, we can see that all the entries are positive, so right off the bat, we know that the Perron-Frobenius theorem applies. Now let's take the vector of x is equal to 1, 1 to the power of t. If we multiply the matrix by this vector, we obtain the same vector again. This means that x is an eigenvector of the matrix, and the corresponding eigenvalue is going to be equal to 1. So this example kind of shows the idea that repeated multiplication by a positive matrix can produce a stable direction, which corresponds to the dominant eigenvector that is described in the theorem. In this case, we saw that the eigenvalues is exactly 1, so the vector doesn't grow or shrink. More generally, the vector might grow or shrink, but we said that the relative proportions between its entries stays the same, which is also what defines an eigenvector. So one famous application of the Perron-Frobenius theorem is Google's PageRank algorithm. Google models the web as a large stochastic matrix where each column represents how a web page distributes probability to the page it links to. If you use Google, you can see that it ranks pages based on a certain algorithm, and that is basically being controlled here by the Google's PageRank algorithm. Using the Perron-Frobenius theorem, we know that this matrix has a dominant eigenvector, so the entries of this eigenvector basically represent PageRank scores, and this measures the importance of each web page within the network. So in this way, a concept from linear algebra is being directly used to help determine how search engines can rank web pages. And that's it. So to conclude, the Perron-Frobenius theorem guarantees that positive matrices have a dominant eigenvalue and a unique eigenvector with positive entries. These properties explain why repeated multiplication by such matrices leads to stable long-term behavior. And also because of the stability, as we mentioned, it plays a huge role in topics such as probability, network analysis, and search algorithms like PageRank. And that is all. Thank you for listening.